In this video, we are going to discuss basic concepts of random variables and distribution functions. The subject of probability theory is the foundation upon which all of statistics is built, providing a means for modeling populations, experiments, or almost anything else that could be considered a random phenomenon. Through these models, statisticians are able to draw inferences about populations. And before going to introduce the concept of random variables, let me explain what is meant by random experiment. If an experiment is repeated under essentially homogeneous and similar conditions, we generally come across two types of situations. One is the outcome or result of the experiment is unique or certain. And second type of experiment is that outcome is not unique, but may be one of the several possible outcomes. Most of the experiments may be of the second type of character. That is, the outcome is not unique, but may be one of the several possible outcomes. This type of experiments are known as a random experiment or non-deterministic experiment. Probability distribution is related to random experiments, and it expresses distribution of probability values over different values of random variable, which is defined over the sample space of the random experiment. Also, it gives us a mathematical expression according to which different values of the random variable are distributed with specified probabilities. So, before going to introduce the concept of probability distribution, let me explain the meaning of the sample space. Corresponding to every random experiment, we associate a set of all possible outcomes of the random experiment. Such a set is called the sample space of the experiment, and usually we denote it by S or omega. So, corresponding to every random experiment, we are associating a set that consists of all possible outcomes of the experiment. And let me give one example of the random experiment and the sample space of that experiment. Usually we consider a random experiment of tossing a coin twice. Suppose we are tossing the coin twice. And what are the possible outcomes of the random experiment? The possible outcomes are this: it may be two heads, or it may be head and tail, it may be tail, or it may be tail and head. So, these are the possible outcomes of the random experiment. And so, S is the set consisting of all possible outcomes of the random experiment of tossing two coins. So, this sample space consists of 4 outcomes. Similarly, another example, suppose we are considering an experiment of measuring lifetime of an electronic equipment. And if we are measuring the lifetime of the electronic equipment, it may be any value from 0 to a finite number. So, any number, that is, it may be in terms of hours, suppose we are taking, it may be any number from 0 to some finite number of hours. So, sample space consists of any real number x, where x is a positive valued quantity, 0 less than or equal to x less than f infinity, that is a finite number. So, these are the two examples of sample space corresponding to two random experiments. First one is the random experiment consisting of 4 outcomes, and second is a sample space consisting of infinite number of outcomes. And now we are defining what do you mean by event. As we all know, sample space is a set. So corresponding to any set, we can construct the subset of the set. So if you are considering the subset of the sample space, that subset are known as event of the random experiment. So event is a subset of the sample space of the random experiment. So event is subset of all sample space. If we randomly, one example I give, if we randomly draw one character from a box containing the characters A, B and C, then the sample space is, we know all possible outcomes are, the possible outcomes are A, B, C, and there are 8 possible events. Why? Because for this set S, we can construct sample subset. It may be either a null set or a set consisting of single outcome A, single outcome B, single outcome C, or it may be a combination of outcomes, that is AB, AC, BC, or combination of all the 3 possible outcomes A, B, C. So for this particular sample space, there are 8 events. So for every sample space, it is possible to construct event of the sample space. And before introducing the concept of the random variable and probability function, let me define one particular class of sets, and that is known as sigma algebra. What is the meaning of sigma algebra? This is a class of subsets of the, and let it be denoted by B, the class of subsets B of S with the properties. The first property is it may be the null set is a member of that set. So null set is a member of the B. Okay. And if A is a member of B, then of course A complement is a member of B. If A1, A2, etc. belongs to B, then union I is equal to 1 to infinity AI is also belongs to B. So first condition is null set phi is a member of that B. If an event A is a member of B, then complement also is a member. So that is claused under complementation. And if A1, A2, etc. are members of the B, then union of, countable union of AIs is also member of B. That is claused under countable unions. So if every class of subsets of sample space satisfying these conditions, 3 conditions, we call a sigma algebra. And why we are defining the sigma algebra? Because we are going to define a function that is known as probability function. What is the probability function? It is a function. So for every function, whenever we are defining a function, there will be a domain and there will be a range. And the probability function is what? The function, and usually we denote the probability function by P, and the domain of the function is the sigma algebra B. The sigma algebra means the subset of the sample space of the random experiment. And the codomain or range is 0 to 1. That is real number in between 0 and 1. And that is called a probability function if that probability function satisfying that function satisfying the properties like this. And what are the properties? One is, suppose A is a member of B, then It's 1. The first condition is this one. This one. Second condition. And if are pairwise disjoint events, then P of so see, suppose you define a function, the domain as the sigma algebra and the range as any value from 0 to 1, and satisfying the conditions. The conditions, one is it is non-negative, that is P of A is always positive for every A belongs to the sigma algebra. And second is P of S, that is the sample space, is equal to 1. And third one, if A1, A2, etc. are pairwise disjoint events in the sigma algebra, then probability of union I is equal to 1 to infinity AI is equal to sigma I is equal to 1 to infinity P of AI. Usually we call these are the axioms of probability, and any function that is defined on sigma algebra with a range as 0 to 1 and satisfying these properties, we call it as a probability function. So, the probability function P assigns a number to each event in B, and so we started from the random experiment, and corresponding to the random experiment we define the sample space, and corresponding to sample space it is possible to construct a sigma algebra, and using the sigma algebra as the domain we are defining a function, probability function P. So, corresponding to any random experiment it is possible to define a triplet, that is the sample space, sigma algebra and probability function, and that triplet is usually known as the probability space. So, when we are defining the random variables or when we are discussing probability distribution, this is the fundamental concept we have to remember. That is, you start from a random experiment and discuss the sample space, and on the basis of the sample space we construct the sigma algebra, and sigma algebra as the domain you define a probability function, and this triplet is known as the probability space. SBP is called the probability space. Now we are in a position to define a random variable. What do you mean by a random variable? See, random variable is also a function. So, for a given probability space SBP, a random variable usually we denote by x is a function with a domain as the sigma algebra, domain as the sample space and the range as the real number. So, the function x is as the function from S to R, and the condition to become this as a random variable is any event, suppose you define AK, this AK, and that is the set of omega are the set events such that x of that omega less than or equal to k belongs to our sigma algebra for every k. So, once again, when we are defining a random variable, we have the triplet as BP, the probability space. A function x is defined with a domain as S and range as the real number system in such a way that corresponding to any set AK, this set of events omega such that x omega less than or equal to k belongs to B for every k. So, this is the random variable definition, and in order to understand the concept of the random variable, let me give one example here. So, a coin is tossing 2 times. So, what is the sample space? Yes, the sample space consisting of outcomes so these are the possible outcomes. And let me define a function x from S to R in such a way that x is the number of heads obtained, for the random experiment. So, if x is the number of heads, that is the definition of that function, you consider this as the outcome x. So, that the number of heads is 2. If this is the outcome, number of heads is 1. Again, if this is the outcome, number of heads is again 1. And if the outcome is this one, number of heads is 0. So, you define a function x from sample space to real number system, and the values of the function are, it may be either 0 or 1 or 2 according to the outcomes, either tt, if it is tt, the value is 0, if it is th or ht, the value is 1, if it is hh, there are 2 heads, the value is 2. So, x is a random variable, having the values 0, 1, 2. So, this is an example of a random variable having 3 values. Hence, the real value x can take on the values 0, 1, 2. Another example, we toss 2 dice, in which case the sample space consisting of outcomes 1, 1, 1, 2, 1, 6, 2, 1, etc. up to 6, 6. So, there are 36 possible outcomes. So, you throw 2 dice, then the possible outcomes are 36, and the sample space consisting of these 36 outcomes. Now, you can define a function x from S to R, and suppose x is defined as sum of numbers obtained. So, sum of numbers obtained, then if this is the outcome, sum of the number is 2. If 1, 2 is the outcome, sum of the number 3, like this. So, finally, if 6, 6 is the outcome, sum of the numbers is 12. So, the random variable x, that is defined as sum of numbers obtained when we are throwing 2 dice simultaneously, then that random variable having the values 2, 3, 4, 5 up to 12. So, these are the 2 examples of the random variable that is having sample space, and corresponding to that sample space we define the function according to certain definitions. After defining the random variable, we are in a position to define an important function, and that is known as cumulative distribution function, or simply distribution function. And what is the meaning of cumulative distribution function? Cumulative distribution function usually denoted by this fx, either f with the subscript x or simply like this. So, a distribution function fx is, that is defined as, this is the definition of the distribution function. Fx is equal to probability of the random variable x less than or equal to x, where x is any real number, And the meaning of this probability x less than or equal to x is nothing but probability of getting the outcome, the event omega in such a way that this x omega is less than or equal to x. So, when we are defining a function f(x) that is probable in terms of probability, that is equal to probability of random variable x less than or equal to x for every real number x, then we call that function f(x) the cumulative distribution function or simply distribution function. And this distribution function have the properties. One, the first property is f of minus infinity, that is the function value corresponding to x when x tends to minus infinity, that is always 0. So, f of minus infinity is equal to 0, and f of minus infinity means limit of f of x when x tends to minus infinity, and f of plus infinity is equal to 1. The meaning of f of plus infinity is limit x tends to infinity f(x) is equal to 1. So, the distribution function f(x) always satisfying these two first properties, that is f of minus infinity is equal to 0 and f of plus infinity is equal to 1. And second property is f of x is always monotonic function, and that is a non-decreasing function, and non-decreasing means for every a less than or less than b, f of a is less than or equal to f of b. So, whenever we have in the real number system we have a value a and b corresponding to this, suppose we are finding f of a and f of b, this is always like this. So, f of a less than or equal to f of b, that is a monotonic non-decreasing function. And regarding the continuity property of this distribution function, f of x is always right continuous, that is right continuous function, and right continuous function means the limit when x tends to h tends to 0, f of x plus h is equal to f of x. So, these are the properties that we have studied while discussing the distribution function, and this is only an introduction of the probability properties of the distribution function I am introducing here. So, and in order to give an example of this distribution function, let me consider the example, the first example itself. That is, the first example, we have the sample space S that consisting of the outcomes So, this is the sample space, and x is the number of heads obtained, and so what are the possible values? It may be 0, 1 or 2. And let me consider the probability of x is equal to 0. What is the meaning of probability of x is equal to 0? X is equal to 0 is possible when the outcome is 2 tails, that is no heads. So, that means probability of getting the outcome Tt. So, when we are getting the outcome Tt, the value of x is equal to 0 is obtained. And what is the probability of getting Tt? Out of the sample space consisting of 4 outcomes, we know, and there are only one favorable case for this one. So, the probability of getting this is 1 out of 4. So, 1 divided by 4. And probability of x is equal to 1. What is the meaning of probability of x is equal to 1? The probability of x is equal to 1 means number of heads is equal to 1. How the number of heads is equal to 1 become obtained? That is, if the event, it may be ht or th. So, if the outcomes are either ht or th, we have x is equal to 1. So, that means out of 4 cases 2 are favorable. So 2 out of 4. So 2 by 4 is the probability of x is equal to 1. And third value of random variable x is c is equal to 2, x is equal to 2. And the probability of x is equal to 2 means it is nothing but probability of getting 2 heads. Probability of 2 heads, if the outcome is 2 heads, then the value of x is equal to 2. So that means out of 4 cases, only 1 is favorable, so 1 out of 4. So these are the probability values corresponding to the random variable 0 value, 1 and 2. So after this, we consider f of x. What is the meaning of f of x? We define the f of x, that is equal to probability of x is less than or equal to x. This is our definition. The definition of f of x is probability of x less than or equal to x. Suppose x is any value less than 0. Suppose x is any value less than 0. What is the meaning of f of x? X is less than 0 means there is no such event of the values, the null set, it is null set, so f of x is equal to 0. When x is in between 0 and 1, when x is in between 0 and 1, what is the meaning of f of x? F of x is probability of x less than or equal to x. That means it may be probability of x is equal to 0. That is only possible case. And so earlier we calculate this value as 1 by 4. And when x is in between 1 to 2, the value of f of x is probability of x less than or equal to x is probability of it may be either 0 or 1. So the possible case x less than or equal to x is x is in between 1 and 2, 1 less than or equal to x less than 2. So the probability of x less than or equal to x is probability x is equal to 0 or 1. So that means this is equal to probability of x is equal to 0 plus probability of x is equal to 1. And earlier we calculated this value, probability of x is equal to 0 as 1 by 4 and probability of x is equal to 1 as 2 by 4. So that means it is equal to 3 by 4. Now the value of this is 2 less than or equal to x. So suppose any value from 2 onwards, then f of x is probability of x less than or equal to x is probability of x is equal to 0, 1 or 2. So that means probability of x is equal to 0 plus probability of x is equal to 1 plus probability of x is equal to 2. So that means this is equal to 1 by 4, 2 by 4 plus 1 by 4, that is equal to 1. So that means we can define, we have the value of the distribution function f of x corresponding to that example is, it is 0 if x is any value less than 0. It is 1 by 4 if x is like this, and it is 3 by 4 if x is just 1, and now it is 1 if x is greater than or equal to. So So, corresponding to the random experiment of tossing 2 coins, and if x is the number of heads obtained, the distribution function corresponding to this is obtained as this is the function. So, when we are discussing a random variable x based on the sample space of the random experiment of throwing 2 dice, tossing 2 coins, then this is the probability distribution function. Similarly, we can find the distribution function of this case also. Suppose consider random experiment of tossing 3 coins simultaneously and x be the number of heads obtained, the sample space consisting of 8 outcomes, and a probability corresponding to each x is the number of heads obtained, then corresponding to that x can have the values 0, 1, 2, 3. So, the values of the probability we can calculate, that is probability of x is equal to 0 is 1 divided by 8, probability of x is equal to 1 is 3 by 8, probability of x is equal to 2 is 3 by 8, and probability of x is equal to 3 is 1 by 8. And as we discussed in the case of the first example, here also we can construct the probability distribution function, and after discussing the definition of the distribution function, we know how to find the values of the distribution function. So, the distribution function values are, it may be 0 if the random variable value is less than 0, x less than 0, 1 by 8 if it is in between 0 less than or equal to x less than 1, it is 4 by 8 if 1 less than or equal to x less than 2, 7 by 8 if 2 less than or equal to x less than 3, and 1 if x greater than or equal to 3. Similarly, we can construct probability distribution function for every random variable, and here we discussed only discrete type of random variables, and we will further discuss the distribution functions of discrete random variable and probability distribution functions in next modules. So, we will wind up this module, and thank you for listening this class. Thank you.